So next, let's do a problem involving the Young's modulus and elastic properties of materials, as it's called. So in this problem here, we're going to have a wooden support beam, which is holding up a deck. And that beam is, let's say, has a square cross section, 10 centimeters by 10 centimeters, and is 3 meters in height. And that beam is placed beneath the deck. So how much load can that beam take before its length changes by 1%? Because for most materials, if the length changes by more than like 1%, you start to get into problems, and you start to kind of have issues. But anyways, let's calculate how much kilograms of deck can this beam actually support for if a 1% change in length is okay. All right, so let's start by drawing a free body diagram just to organize our thoughts. I mean, this isn't really an F equals MA problem, but it's still useful to start with F equals MA on these problems just to figure out what's going on. So I have a beam like this, and it's got some load placed on top of it up here. So there's the deck. And in terms of the forces here, what's going on is the deck is pressing down on this beam with some force, which is going to be equal to the weight of the deck plus the weight of the beam, actually. But we'll just call it mg because we're just asked to calculate the total load it can support. And then there's going to be, you know, a third law pair for that, which is the force that the beam exerts to hold up the deck, which is the whole point of putting this beam here, is we want the beam to hold up the deck, but by Newton's third law, if the beam is holding up the deck, that means the deck is pressing down on the beam, so the beam is going to get compressed as a result of this. So it's going to be a compression type force, and that compression is going to be equal to the load that it's asked to bear at equilibrium. Okay, so that was just kind of organizing my thoughts about what we're actually doing here. Notice also that the force is vertical. The force that's being exerted by this beam and on this beam is vertical. So if you think about the cross-sectional area of this beam, you have to picture this three-dimensionally, something like this. So it's going to have a square cross-section. It's going to have a square cross-section like here. Not a very good drawer, but here we want this area of this square that's perpendicular to the direction that the force is going. So the dimensions of this beam are, it's 10 centimeters in this direction and 10 centimeters in this direction and 3 meters in this direction. So in other words, the area of the beam, the cross-sectional area of the beam perpendicular to the force is going to be 10 centimeters times 10 centimeters. So that's going to be 0.01 square meters. The length of the beam, now the length in this business is taken in the same direction that the force is acting, perpendicular to the area. So the length of the beam is going to be the 3 meters, which is the length of the beam. They also tell me in the question here, they tell me that the Young's modulus of Douglas fir is 13 GPa. I haven't explained that unit yet, so I better do that. Normally, Young's modulus is quoted in units of gigapascals. A pascal, if you haven't encountered that unit before, is a Newton divided by a square meter. So that's the units that Young's modulus works out to be. So 13 gigapascals would be 1.3 times 10 to the 10 Newton divided by square meter. 10 to the 10 came from giga is 10 to the 9, and then it's 13 So I need to move it one extra space to make it 1.3, and then it becomes 10 to the 10. So the Young's modulus is 1.3 times 10 to the 10 in SI units. Young's moduli are, in fact, quite big usually. Gigapascal is like a normal range. Okay, the other thing I was given in the question is that I want the length of the beam to change by 1%. This is what I was talking about with strain in the previous video. What that is telling me is that delta L over L0 is going to be a 1% change. Okay, now if I gather all this information together, remember that my starting equation was F equals YA delta L over L0. So group delta L over L0 together. This is 0.01. So then I have Y, which is 1.3 times 10 to the 10. Let me just drop the units because I don't have a lot of space here. A is 0.01. And then delta L over L0 is also 0.01. So actually we just need to, so it's going to be 1.3, and then times 10 to the 10, times 10 to the minus 2, times 10 to the minus 2. So that'll be 1.3 times 10 to the 6 newtons. And then finally, we were asked for the load in kg, not the force. So we'll set this equal to mg. So then m equals this divided by 9.8. So 1.3 times 10 to the 6 divide 9.8. So we get, yeah, it's still about 1.3 times 10 to the 5 kilograms. So about 130,000 kilograms, which, you know, I don't know if a 1% change is actually a realistic amount for this particular material. But if it is, that would be the maximum amount of weight that this column would be able to bear, hypothetically. By the way, take-home message about this style of problem. The most important thing to be careful about, I think, is the geometry of identifying A and L0. Sometimes it's not so obvious which, like we were given 3 dimensions here, but we weren't actually explicitly told which one's the length and which one is the cross-sectional area. So you've got to figure that out by actually visualizing the situation, which way is the force actually acting, and make sure that your cross-sectional area is perpendicular to that and your length is parallel to that. Other than that, these are pretty much, you know, just sort of plugging numbers into this formula for the most part.